This is gonna be all in one go. Weeks 1 to 4, the 5 to 10. I'll do specific recording for each section afterwards. So let's get right into it. So first off, uh, before the midterm, we studied quizzes 1 to 5, of which consisted of design ether channel and FHRPs, IPv6, OSPF concepts, OSPF configurations, and OSPF v2 multi-area. Now, let's get started with the chapters slash slide decks ahead. So, starting off, we're at Ether Channel and HSRP review. So, this is concepts from last year. Link aggregation concepts. Ether channels can be formed by PAGP or LACP. PAGP, also known as Port Aggregation Protocol, is a Cisco proprietary protocol. Now, its modes consist of on, desirable, auto. The valid modes are auto and desirable, or desirable and desirable, in order to create an on link. For Link Aggregation Control Protocol, LACP, this is multi-vendor. Now, modes consist of active, on, passive. Valid modes consist of active and passive and active. Now, forming an ether channel requires some guidelines, so it is quite simple to understand. Same speed and duplex mode. All interfaces in a bundle must be assigned to the same VLAN or configured as a trunk. Trunks must support the same range of VLANs. So here's an example of it being configured. So the same port speed. So basically making sure it's the right port here. It's quite easy to understand. And then configuring it in range and then the range of interfaces. And then the mode you would like to set. And then this is how you set it accordingly to the steps above. So, and then verify doing show interfaces port dash channel and then the number and then show ether channel summary. Now, first hop redundancy protocols, so FHRPs, if FHRP protocols, so they consist of many types, of which is HSRP v6. So basically, the IPv6 and the IPv4 versions. So HSRP, VRRR, so VRRP, and then GLBP. So three types here. So let's go through the first one, which is Hot Standby Router Protocol, HSRP. This is a Cisco proprietary FHRP. Now this is basically a virtual IP and a MAC are shared between active and standby router. The HSRP active router routes packets. The HSRP standby router waits for the active router's failure to then take over role as the active router. To verify this, you could do hashtag show standby. HSRP v6 operates in the same way as the previous. Now, moving on, VRRP v2, also known as Virtual Router Redundancy Protocol version 2, is a non-proprietary and is a standard protocol across vendors. Dynamically assigns responsibility of one or more virtual routers to the VRRP routers on a IPv4 LAN. Basically, one router is elected as a virtual router master. All other routers act as backups until the master fails. The VRRP v3 is the same thing as VRRP v2, just for both IPv4 and IPv6. Next, you have GLBP, which is Gateway Load Balancing Protocol. This is another Cisco proprietary FHRP. Protects data traffic from a failed router or circuit through load balancing between a group of routers. Basically, just remember the LB part, load balancing. It is a gateway load balancing protocol. Basically, sharing, um, um basically protecting your data. Uh, yeah. Just remember it uses load balancing there. So again, for GLPP for IPv6, it's self-explanatory. It's for IPv6. Okay, now let's go on to the HSRP versions. So we have HSRP v1, which is the default. According to the lecture, no longer default. It is different on different devices, as we have seen within the labs sometimes. So HSRP v1 consists of group numbers 0 to 255. The multicast address is 224.0.0.2. The virtual MAC address, the last two digits consist of 0 to F group number. Does not support MD5 authentication. HSRP v2, you could set this through commands. Group number 0 to 495, 4095. Multicast address is 224.0.0.102 or FF02 colon colon oh colon colon 66. Virtual MAC address is last three digits are consist of 0 to F group number. And HSRP v2 supports MD5 authentication. Now for HSRP priority and preemption, active and standby are determined by election. Election that is done by the highest priority. The default priority for HSRP is 100, or the highest IP address, or the active one. Now to configure HSRP, you do hashtag standby and then the group number and then priority and then the number you'd like to set. Remember the default is 100. Now the highest priority will be chosen as the active and then the second highest will be standby. And then preempt here and then drop P there. Verify by hashtag show standby brief. Don't won't see this because we're mostly focusing on OSPF elections. So, anyways, moving on. Looking at network design, this was covered not as much in the midterm, so most likely not as much in the final, but we must get through this. So, borderless switch network. So this is module 11 of network design. So new slide deck. So Cisco Borderless Network is a network architecture that can connect anyone, anywhere, anytime, on any device securely, reliably, and seamlessly. So basically a hierarchical framework unifying wired and wireless access that is scalable and resilient. That is the keywords. We're making sure that, we're able to make it modular, that we could swap out components if there are failures. So there are three notable areas. So we have the access layer, which is the network access to the user, switches that connect to the distribution layer, switches. Now look at the distribution layer. This performs routing, quality of service, and security, limits layer 2 broadcasts, switches that connect to access layer, and core switches. Now the core layer is the backbone of the network, provides fault isolation and connectivity. Now we have um, two different types of campus networks. So we have the three-tier campus network, requires access, distribution, and core layers. So this is done in an extended star network, as it is recommended to have a centralized focus. The second one is a collapse core, a two-tier campus network. So this consists of smaller campus locations or sites of one building. Combines both the distribution and the core layer. This is, remember this, collapse core. This is referred as the collapse core. Alright, so now switch networks are essentially provide flexibility, security, quality of service, traffic management, and are of a hierarchical design. So again, scalable networks, why do we do this? So we plan for redundancy, minimize the possibility of a single point of failure. The solution is to create redundant paths, alternate paths in case of disruption, may cause logical layer 2 loops requiring STP to address that issue. You may increase bandwidth within a network to make it more scalable through Ether channel or link aggregation. Ether channel can load balance between links, combining existing switch ports into one logical interface. So now there's a section of switch hardware within this section, but it was not covered within the midterm, therefore cannot see it much. But essentially, just remember there are different types of hardware suited for different locations, providing the necessary reliability services that are seen typically in a workplace. Let's say in a mine, they would require, high-speed internet. There you go. There are specific hardware for that. So moving on. Network troubleshooting, module 12. This looks at physical topology, logical topology, basically how we design networks. Um, it's quite simple. Basically, physical topology is how it looks like in real world. Logical topology is how it operates um, logically, right? As a switch, the devices in the network, how it looks like, how it sees each other. So our data management measurement commands, well, we don't have to go through there. There is a troubleshooting process. It consists of 7 steps. 1. Define the problem. 2. Gather information. So look at targets, which are PC, switches, routers. You do with the gather information section. Number 2. You ping, traceroute, telnet, show commands. Basically gathering information. 3. Step 3. You analyze the information. 4. You eliminate possible causes. 5. You propose a hypothesis. 6. You test the hypothesis. And 7. You solve the problem and then document the solution. Now, troubleshooting with OSI and TCP/IP stacks is quite simple. Basically, you could work your way up and work your way down. This is just as reference for the below method. So, one, which is layer 1, which is physical layer, looking at the hub, cabling. The second layer, data link. Looking at the standard switches, basically the layer 2 networks, devices. Layer 3, which is the network layer, looking at router, MLSs. Layer 4, stack 4, transport layer, looks at router MLSs, looking at the packets that are being sent. 5 to 7, end system/application issue. Now, there are structured troubleshooting methods, of which make sense when you read it. So bottom up, basically physical or spanning tree issues. Top down, simpler issues such as software issues. Divide and conquer. Start at layer 3 and test both directions. Follow the path. So this is reduce the scope by tracking traffic path, such as routing looping problems. Substitution, basically swap the problematic device. Comparison, compare with a working device. Educated guess, this is not recommended because you should properly document where you are. Moving on, we're at the next slide deck. Again, the IPv6 basics. So this is for quiz 2. So the previous was for quiz 1. This is now quiz 2. So why IPv6? So there are 3 limitations of IPv4. So basically, first being IPv4 address depletion, second increased network complexity, and then the slide omitted something else, but you get the idea. IPv4 is becoming limited. It was seen as an end-all solution, but in reality, we required more addresses, and it became far too complex for engineers to handle. So therefore, IPv6 was developed by IETF to overcome the limitations of IPv4. IPv6 improvements consist of increased address space, so 128-bit address compared to the 32-bit address of the IPv4, and then improved packet handling, basically a simplified header with fewer fields, eliminates the need of network address translation. Basically, there is no need for public or private addresses like with IPv4. So your IPv6, you only need one IPv6 address that can be routed between public and private networks. So IPv6 versus IPv4 header format. Before we get into that, let's look at the advantages of IPv6 over IPv4. Again, simplified header format allowing for efficient packet handling. Auto configuration for IPv6 using Slack. Basically, it can auto configure its own IP address. Larger address space. So, since it uses a 128-bit address and in hexadecimal, there are so many combinations of addresses that it is impossible to run out. Now, differences between IPv6 and IPv4. The version, of course, IPv4 is 4, IPv6 is 6. Internet header lengths, IHL, basically um, the amount of additional options within a header. IPv6 does not have it, as it is fixed at 40 bytes. Type of service, IPv4 is type of service versus IPv6 of traffic class. IPv6 flow label. IPv6 identifies the packets in a common stream. Fragmentation. IPv4 fields are for fragmentation and reassembly. IPv6 does not contain um, fragmentation. It uses MTU, sends packet back if MTU is too big, and then requests a specific MTU size packet. IPv6 next header, this is something unique to IPv6, identifies protocol carried. Now, this is an important thing to note. IPv4 uses TTL, time to live, whereas IPv6 uses hop limit, which was renamed to be more accurate. But essentially, both of them functions by this. Set by the source, every router in the path decrements the hop limit by 1. Once it reaches 0, the router drops the packet. Source and destination address, again, IPv4 is 32-bit, IPv6 is 128-bit. So ICMP v6, Neighbor Discovery Protocol, RFC 4861, probably not going to remember that. ICMP, also known as Internet Control Message Protocol for IPv6, so ICMP v6, defined in RFC 4443 and 4861. Much more robust than ICMP for IPv4. Why? Because it has new functionality and improvements, more than just messaging, but how IPv6 conducts business. ICMP v6 Neighbor Discovery Protocol consists of 5 packet types. Router solicitation. Host requests IPv6 routers on link to generate RA immediately, so router advertisement. So remember, we have RS, RA, and S. So RA, which is router advertisement, RA is sent to the host with dynamic address allocation, IPv6 prefix length, and default gateway, basically sending the information with basically sending information to the host with its um, dynamically assigned address. And then neighbor solicitation and S is a discover link layer MAC, um, performs host to host ARP. Again, neighbor advertisement and A is between host to host ARP. Response to link layer MAC address request. Oh, MAC request, yeah. And then redirect message router to device messaging. Now IPv4 and IPv6 coexistence. Here are some migration techniques. Dual stack, so both IPv4 and IPv6. Tunneling. So you can do tunneling. So basically, an IPv6 packet is encapsulated inside an IPv4 packet, so that it could travel across an IPv4 network. And then once it has finished crossing IPv4 network, it then decapsulates and then is able to travel across IPv6 network. Right? Makes sense. And then translation, NAT64. IPv6 address representation, again 128 bits. Remember the rules in compressing address, omit leading zeros, and then do a single double colon for a row of zeros. I remember this, shouldn't be too hard, so let's move on from there. So, we have IPv6 types. There are three types to note. We have unicast. So this is first unicast, of which has multiple addresses within it. So let's get right into it. So we have global unicast. So example is 2000 double colon slash 3 link dash local. This is something quite familiar. FE80 double colon slash 10. So it can consist of, like, let's say FE81, FE82. You get the idea. Um, Remember, prefix determines the network, and then afterwards is um, the possible addresses. So the global unicast address is the one assigned to an interface. Link local for link global, right? And then loopback address example is double colon 1 slash 128. Unspecified is double colon. Unique local address FC00 double colon slash 7 to FDFF double colon slash 7. Unique local addresses are not routable to the internet. Limited to areas within a site or inaccessible devices. Then we have anycast addresses, which is a unicast address assigned to more than one interface. Routes are routed to the nearest interface. Let's say for a whole group of a whole area, right? So and then embedded IPv4 double colon slash 80. Second is multicast address. So we have assigned versus solicited node multicast. So assigned multicast is FF00 slash double colon slash 8. So um, at the end of the double colon FF02, we have 1, 2, 5. 1 considers all IPv6 addresses. 2 is all IPv6 routers. 5 is for all OSPF v3 routers. Solicited node multicast is FF02 double colon 1 colon FF00 and then quad 0 slash 104. This is used by ARP. And then we have Anycast, nearest interface having the address according to the routing table. So note that IPv6 does not have a broadcast address. Now, very important part to IPv6 is EUI64, of which is how you dynamically assign yourself a IP address. Um, so EUI64 can be configured on the interface using hashtag IPv6 address and then your address here, and then EUI64. This uses the MAC address of an interface to create a 64-bit interface ID. Yeah. So calculation steps. Essentially, in the middle of your area here, so that is here, you insert FFFE, and then you change the 7th bit. You flip the 7th bit, so it turns on or off depending on the state it was previously. So example of it being done. It's quite simple. I had it down. So moving on. IPv6 and default routes. So configure IPv6 static routes. So we have IPv6 unicast routing. So to create a recursive route, you do IPv6, and then the IP address, the IPv6 address, and then the next hop. So basically, this is a next hop static configuration command. For directly connected, you do IPv6 route and IPv6 address, and then the exit interface. So this is how you do it through like a specific interface, hence the directly connected. Then we have fully specified static, so IPv6 route, and your your destination address, IPv6, and then exit interface, and then the next hop, IP, because it includes the exit interface and the next hop, making it fully specified. Now for a default static IPv6, it is IPv6 route, double colon slash 0, and then your your not your destination, um, the exit interface IPv6 address or the exit interface itself. Now you could verify this via show IPv6 route static. Configure IPv6 floating static route, you do IPv6 double colon slash 0, and then the destination prefix, and then the administrative distance afterwards. The smaller the AD, the more trustworthy it is. One default is 1. Now, here are some examples. 90 is for EIGRP. OSPF is 110. RIP is 120. Can be increased on static to make route less desirable. So let's say I want a floating, I'll make it 5, and then it'll be a less desirable route. So there we go. Now IPv6 dynamic addressing, so DHCP v6 and Slack. So there are 3 different types. It was quite easy to remember. We have Slack, stateless DHCP v6, and stateful DHCP v6. So Slack, just remember, it starts off with stateless. This one starts off with stateless, and then the other one you can remember from its own. So stateless address allocation, or known as Slack, generates IPv6 from its own interface ID. So using EUI64. Stateless DHCP v6, Slack generates interface ID from the DHCP v6 server router advertisement. And then stateful DHCP v6 generates interface ID from DHCP v6 server, but will be managed, basically remembered by the DHCP v6 server. Then here's, they say using external server for stateful and stateless. Quite simple, just using information from the router advertisement, but it will not be fully remembered by the server. So single area OSPF v2 concept. So this is for quiz 3. Previous was quiz 2. So going through this, there you have to remember this tree. Let me expand this a bit. So just remember, I remember for a question. Yeah, so we have dynamic routing protocols, of which there are 2 subsets. There is interior gateway protocols, IGPs, and then the right side, exterior gateway protocols. Sorry. And yeah, I could go through it in depth, but there was a question in regards to what protocol was used for between um, areas, of which BGP was the answer. So yeah. So here was something of note. So dynamic routing protocols, basically they help discovery of remote networks. They maintain up-to-date routing information. They choose the best path and are able to find a new best path if it is no longer available. Now, between IGPs and EGPs, uh, IGPs like OSPF, EIGRP, ISIS are used between autonomous systems, whereas EGPs are used between routing between autonomous systems. So BGP is used for routing between autonomous systems. Highlight that. Now, distance vector routing protocols are based on distance. They say how far it is to the destination network. Vector, it's quite simple. Direction of next hop router to reach destination. Protocols include RIP, RIP, V2, ERGP, and then here, link state routing protocols, of which is OSPF, by the way. Link state router uses link state information to create a topology map. To select best path to all destination networks in topology, does not send periodic updates. Updates only sent when changes are made in the topology. Now, here we have classful routing protocols. So OSPF is considered a classless routing protocol, so thereby it includes a subnet mask in routing updates, and it supports VLSM. Routing protocol metrics, OSPF is based on its cost is based on cumulative bandwidth, least, not west cost. Okay, yeah. Essentially, for routing protocol metrics, the best path is the path of the least cost. Like a highway, right? You want to take the route that takes the less time. Now, onto OSPF features and characteristics. So, OSPF, which is short for Open Shortest Path First. So, this is an interior gateway protocol. It's a link state routing protocol. It is a classless routing protocol, uses area concepts to control routing update traffic. Updates only when there is a change in network topology. Now, a link refers to an interface on a router, segment connecting to routers, stub networks such as the Internet LAN connected to a router. Now, as for components of OSPF, there are 5 OSPF message types, or packet types. So you have 1, the hello packet, 2, the database description packet, DBD packet, which is known as the DBD. Third is a link state request packet, LSR. Fourth is a link state update packet, LSU. Fifth is a link state acknowledgement packet, LSA. Now, OSPF commands to display the tables. So there are 3 types of tables. The adjacency database, which is the neighbor table. This is done through hashtag show, sorry, not hashtag, but you know what I mean. I'm trying to show the command interface here. Show IP OSPF neighbor basically shows a list of neighbor routes, hence the neighbor table, adjacency database. List of neighbor routers with bidirectional communication, unique to each router, basically who the router sends hellos to. Linked state database, topology table, is done through show IP OSPF database. Information contains information about all other routers. It is identical LSDB, so link state database LSDB, across all uh, contained within the OSPF areas. Basically, based on received LSAs, should be identical across all. Now the forwarding database routing table is done through show IP route. Lists of routes generated by LSDB algorithm is unique to each router as it is consisting of where to send packets. Now OSPF commands to display tables. Again, show IP OSPF neighbor for the neighbor table. Show IP OSPF database for the topology table, and then show IP route for the routing table. Now, for the topology table, also known as the LSDB table or the link state database, this is built upon the results of Dijkstra's shortest path first, SPF, of which is the cumulative cost calculation to reach destination. SPF algorithm builds the SPF tree, calculating then the best routes. Now, single area OSPF, routers in one area, of which, if it's single area OSPF, consisting of only one area, area 1. Sorry, not area 1, area 0. Multi-area OSPF, this subsection. So it is essentially the implementation of multiple areas. All must connect to a backbone area, area 0. Now, its advantages include smaller routing tables, reduced link state update overhead, reduced frequency of SPF calculation due to the fact of what it does. It splits calculations between each area. Now, OSPF packets. So, hello packet. So we're going through the 5 packet types that we have listed before. Let's see if I can remember. Hello packet. Then we have the database packet, DBD packet. Then we have the LSU. Okay, LS. Okay, now it's LSR packet. So LSR, LSU, LSAC packets. So again, packet 1 is hello packet for OSPF packet types. 2 is DBD. 3 is LSR. 4 is LS2. 5 is LSAC. Now, let's go through each type. So, the first one, hello packet, discovers neighbors and builds adjacencies. So, it advertises the parameters on which 2 routers must agree to become neighbors, such as timers agreement. The hello and dead intervals must match between them. And it will elect the DR and BDR on multi-access links and Ethernet links. If it is a point-to-point, there's no need for a DR or BDR election. Now, database description packet, DBD, checks for database synchronization. Basically, remember the topology table, it must be consistent between all tables, between all devices within the areas. So this is how it checks. LSR, so link state request, request specific link state records from router to router. Link state updates, of which link state updates contains LSAs, link state advertisements, contain specific link state records, can contain up to 11 different types of OSPF v2 LSAs. But for our case, we only go from LSAs 1 to 5, LSAs LSAs 1 to 5, and 7. So let's go through each LSA. Let's start from the naming and then going through each one individually because this is quite important and I'd like to remember this. So LSA 1, so this is known as the router LSA. This is sent by new routers to announce itself. It's basically a hello packet. LSA, oh shoot, I did it wrong. Okay, let me go back again. But essentially, LSA1 is quite easy to remember, but we'll go through it again. LSA2 is the network LSA sent by the DR. LSA3, summary LSA, is sent by the ABR. LSA4 is sent by ABR. LSA5 is sent by ASBR. LSA type 7 is sent by ASBR. The LSA1, again, that's a hello packet. LSA2, so the origin is from the DR, basically sends out who is the DR. LSA3 is sent by area border router. Oh yeah, should go through what ABR, DR means, so DR is designated router, and then the ABR is the area border router. ASBR is autonomous systems border router. If I recall, we'll see later on. So ABR, so LSA3 ABR sent by the ABR summarizes routes between areas. Yeah. So LSA2, by the way, is for basically to get information for that area, and then here routes between areas. Now LSA Type 4 is an ASBR LSA summary ASBR. That's it, LSA. The origin is from the ABR, and it basically says who is the ASBR, our connection to the outside, summarizes routes to outside networks as well as between areas. LSA 5 is known as the external LSA, of which the origin is from the ASBR, basically routes coming into the system. LSA 7, external NSSA LSA, which is non-stubby uh, network something. Stubby something. Yep. Origin is from the ASBR. Basically, mass stubby areas by taking in external routes. Basically, so from a stubby network within an area. So not um basically let's say a stubby network uh sends in packets from alternate source. The ABR then converting it back into a LSA Type 5 to send back to the backbone. Yeah. I'll do a separate video of doing LSAs. And then link state acknowledgement LSAC acknowledge the other packet types. Oh, that was a long one. Take a little voice break. Okay. So OSPF devices. Here. So I was right. So we have OSPF devices. So we have DR, which is the designated router, elected based on priority, highest priority, or highest router ID. And then the BDR, which is the backup designated router, the second highest priority or router ID. Now, ABR is an area border router. It is between areas, containing multiple areas on interfaces. Sends LSA Type 4s. ASBR, the autonomous system border router, the router routing to the outside. And then every other router not assigned a role. They say who was not assigned a BDR or a DR. Okay, now we have OSPF operation. So this is another important area. So we'll go through it together slowly. I'll say the name of each operational state. So I believe there's 1, 2, 3, 4, 5, 6, 7. So let me take note, 7 states. So there are 7 states for the OSPF operations, of which consists of down, init, two-way, exstart, exchange, loading, full, or known as I like to do it as DI2 EELF. So DI2 ELF. Yep. Okay. So down state essentially no adjacency hazard for the init state. This is known as a transit state, so it is transitioning. Won't be on there for long. Router received a hello packet sent through the multicast address 224.0.0.5 only for OSPF v2 routers. And then we have two-way, which is a stable state. It has established bidirectional communication. If it is a multi-access connection, it performs a DR/BDR election. Now we have the exstart state, the transit state. If it is a point-to-point network, it will determine master and slave router, of which is based on the router ID. Then we have the exchange state, which is so extern and exchange are transit states. For the exchange state, it shares link state database packets. Comparing to a database, if they are not the same, then they will transition to loading. If they are the same, they'll complete the synchronization and transition to full. So after the exchange state is the loading state, which is a transit state, performs LSR and LSU exchanges for additional information. Routes are processed using the SPF algorithm. And then for the full state, this is a stable state. It has completed full synchronization. And then here, why do we do DR elections? So multi-access issues consist of creation of multiple adjacencies, thereby increasing the number of LSAs, and then the number of adjacencies increasing according to this formula here, i.e. a lot of floodings of LSAs in a network, extensive flooding, right? So designated router functions and election, so DR, BDR, and druthers. So DR is for the collection and dissemination of LSAs. BDR is the backup. Druther is every other router within that area. So default DR election process, so highest priority. If same, transition uh, to 2. And then highest router ID, of which looks at the highest router ID, of which is manually configured, or yada yada, which is on the next section, but essentially highest router ID, of which consists of the highest manually configured, or true uh, highest loop back in up slash up, or third highest interface up and up. So next module. So single area OSPF v2 configuration module 2. This is for quiz 4. So OSPF router ID. So the RID. So within to set it up, you do router OSPF and then your ID. The process ID. The process ID is locally significant, but the best practice is to have the same process ID on all OSPF routers. So let's say I use router process ID of 10, so thereby router OSPF 10. I use this across all my OSPF enabled devices. So there we go. However, the router ID is unique to each one. So router ID creation requirements is what I quickly covered before. So manually configured. If not, second highest loopback interface. It is recommended to have it as a /32. So this is the best practice to configure a router ID for a device. And then make sure there's no network address route. Uh, I don't know what I mean here. Okay, so third, the highest IPv4 address interface in the up and up state. So router ID configuration for a device, you do router dash ID and then the address, 32-bit address you like to insert. So there we go. Now, remember mentioning point-to-point OSPF networks, enabling OSPF on interfaces. So this is how you enable OSPF. This is how you advertise your areas. Uh, so network and then your network address, wildcard mask, and then your area and the area ID. That's how you advertise your interfaces. Now, your best practice for the area, well, making your OSPF is to have area 0 for the backbone. Alternatively, you can configure OSPF directly on the interface with, so once you, let's say int gigabit 0/0/0, and then you do IP OSPF. This is a really faster way of enabling OSPF directly on the interface. Now, interfaces that are configured with above methods are now able to send and receive OSPF packets, of which we covered before. Wildcard mask, again, I've covered this before. Basically, all network bits are off, all host bits are set to on. Network advertisement configuration. So you could do this through the wildcard method. So network, and then doing the specific wildcard calculation for that specific network. The IP address is up on the interface area and the area it is currently in. Look to your topology map. And then to a network command, so using quad 0, basically network, and then your address, and then 0.0.0, quad 0, right? And area, and then your number, and then configure OSPF directly on the interface. So IP OSPF, and then your process ID, which is shared across all participating in the OSPF area, and then area, and then your number. Uh, Now, very important, passive interfaces stops messages heading towards loopbacks or end devices, prevents OSPF routing messages from being sent, um, basically prevents inefficient use of bandwidth, inefficient use of resources, and prevents increased security risk. Now, to configure passive interface, there are two ways of doing it. You could configure a passive interface for each interface. So you could do int range and then passive dash interface. Wait, no, sorry, not in. Oh yeah, passive dash interface, and then the interface you would like to. This is done within um, the router configuration terminal. Here, router passive dash interface, and then the interface you like to set as passive, or set it as default. So passive interface default in the router OSPF, but then it sets them all as passive. So therefore, you have to do no passive dash interface, and then the interface that you've configured beforehand. And there we go. Now for OSPF point-to-point networks, network type. Election is unnecessary on point-to-point networks. Consists of only two networks on the Ethernet segment. DR/BDR elections are done on Ethernet interfaces, not for serial links. Very important. Want to set up point-to-point to allow faster convergence, as you don't have to do elections. So configuring a OSPF point-to-point network is quite simple. You get on the interface and then you do IP OSPF network point-to-point. You have to do this for both sides. Loopbacks can be configured as point-to-point to advertise a full network, basically simulating a real LAN. And then you verify this through show IP OSPF interface, and then the interface you have configured the point-to-point on. Now we have multi-access OSPF networks and DDR elections. So OSPF multi-access network, one router, DR, controls distribution slash dissemination of LSAs. No other DRs within a network. So example for routers surrounded by a switch. So OSPF, designated router, DR, multi-access networks elect a DR and BDR. DR sends a multicast um, 224.0.0.5 for hello messages for all OSPF routers. BDR elected in case DR fails, passively listening and maintaining relations with others. Druther is every other router in the topology. Uses multicast address 224.0.0.6 to send OSPF to the DR and BDR only. Verify the roles via show IP OSPF interface and then interface configure. Okay, so verify the DR and BDR adjacencies. Do show IP OSPF neighbor to see whether it is full Druther, full DR, full BDR, or two-way Druther. So if it is full slash Druther, it is DR adjacent with a non-DR or non-BDR router. Full DR is the router adjacent with a DR. Full BDR is router adjacent with a BDR. And then two-way Druther router adjacent to router between routers. Again, the default DR election process in sequential order occurs on every link except serial links. Addition of a new router does not initiate a new election process. This is non-preemptive, very important. This is the non-preemptive process. So one, so highest priority. If it is the same, transition to two, highest router ID, of which router ID is done through the highest manually configured, highest loopback address in the up and up, or highest interface in the up and up. So there we go. And best practice for the loopback one is to have a /32 address for if you're doing an automatic assignment. Okay, so IP OSPF priority configuration. Note that the default value for OSPF priority is 1. Priority 0 prevents an interface from being elected as DR or BDR. So the priority range consists of 0 to 255, and then you configure this via IP OSPF and then the priority you'd like to set. So modify single area OSPF. You can modify it by you could change the default reference bandwidth. So OSPF cost metric, the default cost is 1 for 1 gigabyte per second, 10 gigabytes per second, 100 megabytes. All of these values have the same cost of 1, of which are done through this calculation. I'm not gonna entirely remember, but let's say I have 1 gigabyte per second interface and a 10 gigabytes per second interface, and I want them to be registered as different. I would have to increase my reference cost to 10,000 to match the number of megabytes per second here. So you can adjust this through auto cost as reference bandwidth in the router OSPF or on the interface itself. So best path is chosen. So cost of OSPF route. Best path is chosen on the least costly route to destination. This is done through. You can check this through show IP route. Configure hello packet and dead intervals. This is so that you can match it and according to specifications. Hello packets are sent to all routers 224.0.0.5 every 10 seconds by default. So 10 seconds. And then the dead timers are every 40 seconds. Dead timers are every 40 seconds. Or times. So you do this by IP OSPF hello dash interval and the number of seconds you like. So let's say I want a half for the hello packets. So I want 5, so 5 seconds, and then that dead interval will automatically change. But this is depending on where you're doing this. So best practice, just do it for both, just in case. And then it should be automatically assigned as 20 for for the dead set timer. And note that intervals must match between links again, and you check this with show IP OSPF neighbor. For default route propagation, so default route review, again, this directs packets not explicitly using the routing table. So IP route, and then quad 0, and then it's either a next hop or exit interface. Static route review, manually configured route to a network. Dynamic routing, OSPF, used for network with multiple topology changes. Floating static route, backup route in case of failure. And then here are some route administrative distance values. So when you're configuring it, directly connected is 0, static is 1, 110 is OSPF. Lowest being the most trustworthy. Propagate default static route configuration done on an edge router, which is your connection to outside networks. First, configure a default route using the following. So IP route, quad 0, next interface, next hop or exit interface. Then you may perform the command in router OSPF, router configuration. so config dash router, then default dash information originate. And you verify this via show IP route. And then remember, S star within the table is the static route. O and then star E2 is the OSPF learned route. Now that's it for the weeks 1 to 4. Losing my voice, so I'll take a break. I'll make a separate video for weeks 5 to 10.